heat transfer lecturing. In this video, we are going to study about the problems on the internal flow. How we studied the problems on the external flow. In the same way, we are going to study about. We are going to solve some problems about on the flow in a pipe or a internal flow. I explained in the previous uh, video lecturing, video classes. Now consider a pipe, a circular pipe, and it is a fluid. A fluid is flowing with a velocity of u infinity and a temperature is t infinity. And this wall temperature surface temperature of a pipe is Ts. Both are different in temperature, so heat transfer will be takes place. When all those things already we studied, how the velocity boundary layer and thermal boundary layer formation will be takes place. All those things studied. Once again, I am telling just once again I am doing the revision of that one. That's all. When the fluid is come in contact with the pipe, what will happen? The boundary layer development starts. When the fluid, when coming in contact with the surface, what will happen? The growth of or development of boundary layer will be takes place. Now just consider this is the axis of the pipe or a duct. Finally, this boundary layer is going to meet the center line or axis of the pipe. This type of boundary layer happens completely in the circumference of the pipe. So, complete this pipe or complete this duct filled with the boundary layer after this point. This one you're going to call as the fully developed flow. And up from here to here you're going to call as the entry length or not fully developed flow or a entry length hydrodynamically entry region. Those things we are going to call this area, and we going to solve most of the problem by considering that fully developed flow means a pipe containing a filled boundary layer. This zone from this point to complete in this axis, in the z axis, is going to call as the fully developed flow. This one is not a fully developed flow, but this is entry length. In internal flows also, the different problems it becomes, that is what laminar flow, how you studied in the external flow. In the same here also laminar flow, constant heat flux condition, constant wall or a surface temperature, constant wall or surface temperature. Same thing how what we studied in the external flow, and also the turbulent flow will becomes. Okay, we will check out the equation, which are the equation we are going to using for laminar flow for constant heat flux, constant wall temperature, and turbulent flow. And also in this internal flows, in this internal flows problem, most of the cases it is a circular duct, but in sometimes it is non-circular duct, like a square or a rectangular duct. It may be comes in the problem. See, in that one there is no that much of difficulty will be there. If it is a duct, this is the diameter, and we are going to solve by Reynolds number is equals to rho into velocity into diameter divided by dynamic viscosity, where d is this diameter for the circular duct. Suppose if it is a non-circular duct, like in this case, what we will use means Reynolds number is equals to rho into u into dh by mu, where dh is the hydraulic diameter. That is the difference between circular duct and non-circular duct. There is no any other difference. Here this diameter will be used, but here you call as the hydraulic diameter. This dh can be defined as 4 into cross-sectional area divided by the perimeter. 4 into cross section means length into breadth divided by 2 times of length plus breadth for the this one, for the square. Okay, there is no any difference. Just for the circular duct, this is the D. For non-circular duct, the D becomes the hydraulic diameter. This hydraulic diameter can be calculated by 4 into cross-sectional area divided by perimeter. This one you should be note down it. Now we are going to solve the problem on constant heat flux condition, constant wall condition, and turbulent flow condition. Also one problem on the any one of this duct, whether it may be a square duct or a rectangle. Totally 4 problems now we are going to solve now one by one. Before going to that one, once again we will see the data handbook, how to take the equation. I already mentioned I have the 6th edition data handbook. Same procedure. Our condition is anyhow the properties can be taken by this column for the gases, for the liquid metals, all those things. Now our condition is what? Convection. In that one is we are discussing the force convection, but now we are not discussing the external flow, but this time we are discussing the internal flow. Now you open the corresponding page number. In my data handbook the page number is 123. 123. See here we can see that internal flow, and this is the properties, how to take the properties. In the external flow we called as the film temperature, but in the internal flow we are going to call as the bulk mean temperature or just a T mean temperature. Those things I will be explaining in the problem. Suppose if the Reynolds number comes less than 2300, that is the laminar flow. If it is comes greater than 2003 in a flow in a duct, that is the turbulent condition. Here you can see that if it is less than 2300, that is the laminar condition. In that condition, F can be calculated by 64 divided by Reynolds number. And I told that suppose if it is the entry region problem like that, suppose you have to calculate the heat transfer this also. While calculating the complete heat transfer, suppose you have to consider this also. In that condition, this equation you have to use, entry region. For what condition? Here you can see that constant wall temperature and considering the entry region, that time this equation you should be used. Suppose if you consider a fully developed flow, suppose you are going to neglecting this one, you are considering only this one, and the condition is laminar flow and constant heat flux condition, constant wall temperature condition, that time you have to use Nu is equals to 3.66. Direct the answer will be there. There is no any substitution will be there. If it is considering fully developed flow, you can see here fully developed thermal layer or fully developed flow for constant wall temperature, and for the laminar case you have to take this equation. In the same way, if it is a constant wall temperature, N is equals to 3.66. Suppose if it is a constant heat flux condition, fully developed flow and laminar condition, the Nusselt number becomes 4.36. There is no any equation. This is the constant we will obtain for that condition. Suppose if Reynolds number is greater than 2300, that becomes a turbulent flow. Here you can see that the equation used for the turbulent conditions. Suppose in the problem if they ask find out the coefficient of friction factor, that time you have to go for this equation, depend upon the Reynolds number. If it is greater than 10 to the power of 4, you have to go for this one. For the rough tube, you have to go for this one. Okay. Suppose in the problem surface roughness, this epsilon surface roughness is given, you have to choose this equation. Okay, one or two equations will be there. You go through these equations depending upon the problem. In the problem clearly mention if the surface roughness is some number, then you should go for this equation. Other you can go for 0.25 this equation, or if it is greater than 10 to the power 4, you have to go for this equation. Only you have to be use these three equations in most of the time. And to calculate the Nusselt number, you are using the 2.3.1 equation. This is the very common equation we are using for the turbulent condition. Keep it in mind, T 2.3.1, this is the common equation we are using for the all turbulent flow condition. That is what 0.023 Reynolds number to the power of 0.8 Prandtl number to the power of n, where n is the constant, n is equals to 0.4 for heating of fluids. Suppose here suppose the fluid is coming at 10 degrees centigrade and leaving at 40 degrees centigrade or 60 degrees centigrade. Here the fluid is get heated, in that condition n is equals to 0.4. Suppose for the second condition, suppose if the fluid is entering at 50 degrees centigrade and leaving at 20 degrees centigrade, this is the cooling of the fluid. In that condition you have to take n is equals to 0.3. This is the condition. Okay, for the turbulent flow, most of the cases we are using this equation only. You go through that one. In the laminar flow condition, if it is a non-circular duct, then we have to go for this one. For a non-circular duct, in that condition, laminar and non-circular condition, laminar flow, non-circular condition, in that condition you should go for this one. For a constant heat flux, Nu1 is equals to this much. For constant wall temperature, 3.657. Okay, for different geometry is given. Okay, those are the equation should be used. This is a very simple one compared to the last one, and also problems are the simple one. Now we will solve the problems on laminar flow and these two condition, turbulent flow, circular duct and non-circular duct condition. Here is the problem. Water entering at 20 degrees centigrade means the inlet temperature of water, or the water is entering inside the pipe, is 20 degrees centigrade, is heated to 60 degrees centigrade, means outlet temperature of water is 60 degree, in the tube of 0.02 meter ID inner diameter. This is the diameter of the pipe at mass flow rate of 0.01 kg per second m dot. The outside of the tube is covered with an insulated electric heating element. Try to understand the outside of the tube. Suppose if you consider this is the pipe, the inlet temperature is 20 degrees centigrade and after coming out of the pipe is 60 degrees centigrade, because the outside layer is made up of a what? Electric heating element. This type of condition is used for the heat flux condition. If it is electric, is there, electric term is mentioned, this is nothing but the heat flux condition, or Q is equals to constant, heat flux is equals to constant, that is the condition. And also here also clearly it is given that produces a uniform heat flux. Suppose if it is not given, only the electric element, heating element is given, that is nothing but that is the uniform heat flux condition. And the Q value is given 15,000 watt per meter square over the surface, neglecting any entrance effect. Neglecting any entrance effect means already I discussed, this effect is neglected. Then what is that? You have to consider complete the flow is the fully developed flow. We have to determine the Reynolds number, heat transfer coefficient, the length of the pipe needed for 30 degrees centigrade, the inner tube surface. Okay, these are the sub questions we have to be find out. You go through that one, and also I will take one by one. First we will collect the data carefully, and also I will write the sketch. A pipe, the fluid is entering, you can take TMI or a TM0 or a TMI or a TIR, both are the same thing. The inlet temperature or a mean inlet temperature, both are the same thing. What is convenience for you, take that value. TMI is the entering here, T0 outlet temperature of, here the fluid is water and the cross section is circular pipe. Outlet temperature of water is 60 degrees centigrade and the mass flow rate is 0.01 kg per second. The heat flux over the surface, the Q is equals to 15,000 watt per meter square. These are the data is given, and also the inside diameter is given 0.02 meter. Okay, once you collect the data and writing the sketch, the next step is what? Find out the film temperature. But you cannot tell the film temperature in the internal flows. You have to tell mean temperature. Mean temperature means inlet temperature plus outlet temperature divided by 2. Okay, you should know the difference between the external flow and the internal flow. In the internal flow, you're going to call as the bulk mean temperature. Bulk mean temperature, that is Tm is equals to, you can write Ti plus T naught by 2R, TMI plus TM naught by 2. These terms are used in the our data handbook. It means which is the data handbook we are using. They're mentioned like that. In some textbooks, in most of the textbook, they mention Ti plus T naught by 2. And I also take Ti plus T naught by 2 only. Okay. The inlet temperature is 20 plus 60 divided by 2 is 40 degrees centigrade. Now what you have to do? At this mean temperature, you have to collect the properties of fluid, properties of the given fluid. Here given fluid is the water. Okay. Already I shown that one. Once again, I will show here. Property values, go to the contents. Here you have to choose the water is a liquid, not a gas. Water is the liquid, so go to the page number 21. Here it is given at 40 degrees centigrade you collect, at 40 degrees centigrade you collect all the properties. What is mentioned here, you collect all the properties and write down here. Once in this properties, they given density and kinematic viscosity, but dynamic viscosity is not given. But we can easily find out what will be the dynamic viscosity. If you know the rho value and the nu value, you can easily know it. This kinematic viscosity nu is equals to mu by rho, or mu is equals to multiplying these two things, you will get this value, or only this value is enough. But just I taken to the mu. If it is any for the calculation, it may be useful for the calculation. Just I taken that one. What are the question they ask? First you have to find out Reynolds number and the heat transfer coefficient. Once you collected the data, the next step is the Reynolds number only. Reynolds number is equals to what? Density into velocity into diameter divided by dynamic viscosity. This is the equation, already we know it. The same equation also we can written as what? Velocity into diameter divided by rho by mu, I can written as the nu value. But in the problem, the um is not given. The mean velocity is not given in the problem. But in the problem, it is given as what? M dot is given. The mass flow rate is given. So based on the mass flow rate, we can find out what is the Reynolds number. This is the equation is available in the data handbook. Here you can see that this is the Reynolds number is equals to 4m divided by pi d mu, where m is the mass flow rate. Okay, by using this equation also we can find out the Reynolds number. So I written here the same equation I download as remains. Same equation I written here, copied here. Calculate the Reynolds number. Once you calculate the Reynolds number, you got it as the 979.49. This is what the Reynolds number is, what? Less than 2300. Therefore the flow is laminar. Therefore if it is the flow is laminar, then what we have to do? Flow is laminar, and this is what type of condition? This is the constant heat flux condition. Q is equals to constant. Now see the data handbook. For constant heat flux condition, here constant heat flux condition, fully developed flow, Nusselt number is equals to 4.36. There is no any equation, the constant term will be there. Directly you substitute that term. Nu is equals to 4.36. The equation is 1.27. Next, to calculate the convective heat transfer coefficient, H is equals to di by K, where H is equals to, substitute the values. K you know it, K you know the value, and di is 0.02 meter. Substitute here, you will get H is equals to 136.9 watt per meter square Kelvin. This is the second question what they ask. Next, the third question is, what is the length of the pipe is needed for 30% increase in average temperature? 30% 30 degrees centigrade increase in average temperature. It is nothing but the delta T. Delta T. Delta T means that is T naught minus Ti. The same thing. T naught minus okay, not that one. In the question they're asking that what is the length of the pipe needed for a 30 degrees centigrade increase in the average temperature. Okay, one small correction. Just instead of taking 30, you take it as the 40 degrees centigrade. Okay, that the clearly given the length of pipe needed for 40 degrees centigrade increase in average temperature. This is nothing but what the delta T. Delta T is nothing but what T naught minus Ti is equals to 60 minus 20. That is the 40 degrees centigrade. Here the inner diameter is given, but the length is not given. What is the length is not given. We have to calculate that one for a change of temperature of how much? A 40 degree centigrade. The first two equations is over. Reynolds number is over, heat transfer is over. Next, the third one we are going to calculating that one. The third one can be calculated by like that. See, this is the equation. We know that heat flux is equals to rate of heat transfer divided by surface area. Then Q is equals to Q into AS. You can also written Q is equals to m dot Cp into T naught minus Ti. Now you compare these two equations. We obtained like that. Compare equation 1 and 2. Q is equals to AS, surface area is equals to m dot Cp T naught minus Ti. Next, our aim is what? You are going to find out in the length. What about the AS? AS is equals to surface area is equal to pi into DIL. Now we know in this problem Q is given, heat flux is given, so that's why this equation we using here. Now all the values we know it, substitute all the values, then we will obtain what will be the length. L is equals to 1.7829 meter. After this length, next is the what is the inner tube surface temperature at the outlet. Inner tube surface temperature means inner tube. Here what is the TS naught value or TW naught value? Both are the same. What is the wall temperature at the outlet? The question is asking like that. What is the TS naught? That can be found out by using this equation. You know that one. Q is equals to HAS wall temperature minus fluid temperature. Already we know the fluid temperature, but we don't know the wall temperature at outlet. And we know that Q by AS is the heat flux. Just reducing this equation. Then Q is equals to 15,000. Substitute the values. We will obtain the wall temperature at the outlet. And the fifth question is the friction factor. This is what type of flow? This is the laminar flow. For the laminar flow, the friction factor F is equals to 64 divided by RED. The equation number 1.1. Equation number 1.1. Substitute the values, and we know the Reynolds number. Substitute here. We will obtain this value. Okay, while you calculating the friction factor and substituting the Reynolds number, you will get a 0.065. There is a minute correction you do. The Reynolds number is how much? The Reynolds number is the 979.41. 0.64 divided by 979. You will getting as the 64 divided by 979. You will going to get it as the 0.065. That is the friction factor is obtained. After calculating the friction factor in the problem, next is you have to find out the pressure drop in the pipe. The pressure drop in the pipe can be calculated by the equation is given in the data handbook in the same page number, that is 123 page number, in the same page number. Here you can see this is the equation. You can be calculate the pressure drop due to friction. Delta PF is equals to pressure drop due to friction. Now I am writing this equation and I know all the values. The friction coefficient of friction I know it, rho, LD, all the things I know it except the velocity, because in this problem the velocity is not given. Instead of velocity they given as m dot value, the m dot value is given, that is the mass flow rate value is given. Suppose m dot is given, this equation you have to use. M dot is equals to density into velocity into cross sectional area. Cross sectional area is equals to pi d I square by 4. Now you substitute all the values. Here um is the unknown one. Substitute the values and you finally obtained um is equals to 0.032 meter per second. Now come to this equation. What the equation is taken from the data handbook, just now I shown here. This equation, the same equation you have to be noted on, and you substitute all the values. You will obtain the pressure drop in a pipe due to friction. You will obtain as the almost near to 3.0 Newton per meter square. And the last question is, what is the power required? What is the pumping power required? And the pump efficiency is 50%. This can be obtained by pumping power is equals to just multiply by m dot by rho into delta pf. You will get a pumping power as this much of watt. But this is a 50% efficient, therefore divided by 50%. Finally, the actual power required to pump the pipe in that pipe, that is how much? 6.23 into 10 to the power of minus 5 watt. Now in this problem, what you solved means the laminar flow condition for q is equals to constant. Okay, and also suppose if the velocity is not given, um is not given, but m dot is given, this is the equation we use to calculate the qm. This question is also asked in the examination. Now we'll go for the next problem. Now you considered engine oil at 60 degree centigrade flows. See, here the fluid is what? Engine oil. In the last problem, the fluid is water. In the last four problems, the fluid is the air. In each problems, the properties are changing and you should know how to take the corresponding properties from the corresponding table. Engine oil at 60 degree centigrade flows at 0.5 kg per second. Here also m dot is given. Okay, u is not given. Okay, but you can be calculate the velocity using this m dot. I already shown in the last problem. In a duct with constant surface temperature, see what is the condition is telling? Constant wall temperature, that is TW is equals to constant. That condition is asking here of 20 degrees centigrade. Assuming fully developed flow, means neglect the entry length. We have to calculate what is the heat flux at entry and calculate the pressure drop per meter length for 3 centimeter diameter of the tube. Okay, now we will collect the things. The fluid is the oil and the inlet temperature is 60 degrees centigrade and m dot is 0.5 kg per second and the wall temperature, constant wall temperature is 20 degrees centigrade and the condition is wall temperature is constant and the diameter is given. Just I will write the sketch. A pipe, the Ti is 60 degrees centigrade at a mass flow rate of 0.5 kg per second. This wall temperature is 20 degrees centigrade and the outlet, see here the T naught value is not given. T naught value is not given, but you have to assume T naught is very approximately equal to the T wall, that is equals to 20 degrees centigrade. Otherwise it is not possible to calculate. So assume the water outlet almost equal to the wall temperature of the pipe, so that you consider as a 20 degrees centigrade. Based on that one, now you calculate the mean temperature, then you will get it as the 40 degrees centigrade. At this temperature, collect the properties of the oil from the data handbook. Okay, just you go to the contents, the same thing, liquids. In the liquids you have to search where it is there. Here you can see that engine oil unused is there, that one you have to use. At 40 degrees centigrade, note down all the properties. Just right now I note down here all the properties. Once you know the properties, what is the next step? You have to find out the Reynolds number. Here once again the velocity is not given in this problem. Instead of velocity it is given as what? Instead of velocity it is given as mass flow rate 0.5 kg per second. Therefore you can calculate the Reynolds number by using this equation. This equation is available in the data handbook. Finally obtained as the Reynolds number is 100.5. Therefore this Reynolds number is less than 2300. Therefore flow is laminar, and the given condition is what? Given condition is constant surface temperature. Therefore we have to choose the equation from the data handbook. Laminar, constant wall temperature, fully developed flow. Therefore you have to use Nusselt is equals to 3.66. that is equation 1.22. Equation 1.22. Nusselt is equals to 3.66. Then you know this equation, find out the H value. Once you find out the H, the question is what? You have to calculate the heat flux at the entry. Heat flux at the entry, the equation can be the equation already we used in the last problem. The same equation, H into A is T wall minus Ti, heat flux at the entry of the tube. Then Q by AS is the heat flux. Q is equals to H T wall minus Ti. Substitute the temperature T wall, I know it, and the Ti I know it, the 60 degree. Then we obtain as the Q is equals to minus 7.2 minus 0.7 watt per meter square. And the next question is to find out the friction factor. The same thing, find out the friction factor F is equals to 64, because this is the laminar flow. After find outing that one, substitute to here. And once again you don't know the value of um, but we know the value of m dot. Once you know the m dot value, what is the procedure is there? M dot is equals to density into um into cross sectional area. The same thing what you did in the first problem of the internal flow. Find out what is the um. Now you substitute all the values to this equation. Finally you obtain this answer. Okay, the two problem is solved, laminar flow condition, and I show how to take the equation also. Suppose if it is a constant wall temperature, Nu is equals to 3.66. For a constant heat flux condition, Nu is equals to 4.36, and you have to calculate the which one, the pumping power or a pressure drop delta Pf, that should be calculated by using this equation, where F is equals to 64 by RED, Reynolds number based on the diameter. In the problem, velocity is not given. If it is the mass flow rate is given, we have to use this equation to find out the Reynolds number. Or anyhow, if you know the m dot value, find out the um, then Reynolds number is equals to rho into um into di by mu. By using this equation also you will get the Reynolds number. In both the way you will get the Reynolds number. There is no any confusion between that one. In the problem, if it is m dot is given, find out the what is the um. Then using this equation also you can be find out the Reynolds number. Suppose if it is using this equation also you can be find out the Reynolds number. But keep it in your mind, always one more important data is important note is there. This value Re is equals to 4 m dot pi d mu. This equation used only for the circular ducts, not for the non-circular ducts. Always keep it in mind. Suppose if it is a non-circular duct is given, in that one what the m dot is given, you should not take this equation. If m dot is given, use this equation, rho um cross sectional area, find out the um, then using this um find out the Reynolds number. For non-cross sectional area, this equation cannot be used. This equation is only for the circular duct. Always keep it in your mind. Suppose if you're getting the confusion, if m dot is given, simply you calculate the um, find out the Reynolds number. The problem is solved. Okay, we will go for the next problem. Water at 50 degrees centigrade, here the fluid is 50 degree, and 50 degree enters, 50 degree centigrade enters means the inlet temperature of water, and diameter is given, and 3 meter 3 meter long length is given. L is equals to 3 meter long tube with a velocity of 1.5 meter per second. Here um is given but not m dot is given, so somewhat complication is reduced. In the last two cases m dot is given. If you know the m dot also, you can be find out the um, but here directly um is given. The tube wall is maintained at 100 degrees centigrade, means the wall temperature or a surface temperature is given. Calculate the heat transfer coefficient, means h bar, and also total amount of heat transferred if the water exit temperature is 100 degrees 70 degrees centigrade. This is T naught is given. Calculate the Q value if it is T naught is 70. Now you collect all the data. I will write the sketch. A pipe of diameter is 1.5 centimeter. A fluid is moving with a velocity of how much? 1.5 meter a second. The inlet temperature is 50 degrees centigrade. Inlet temperature is 50 degrees centigrade, and the outlet temperature of the fluid when comes out from the pipe is 70 degrees centigrade, means it is heating. The process is heating, and the wall temperature or a surface temperature of pipe is 100 degrees centigrade. 100 degree centigrade. Okay, almost all the data is taken. Once you collect the data, next step is you find out the mean temperature. Tm is equals to what? Inlet temperature of the fluid plus outlet temperature of the fluid divided by 2. While doing that, 150 plus 70 is 120 divided by 2 is 60 degrees centigrade. Now collect the properties of the fluid. Here what are the fluid is? Fluid is water. So collect the properties of water at 60 degrees centigrade from the data handbook. The first problem I showed how to take the properties of water. Go to the liquid properties, and in that one take the water properties. In the same way I collected all the data here. After collecting the data, next step is you find out the Reynolds number. So when you take calculating the Reynolds number, it is got it as 47,000. 47,000. That is what, this is greater than 2300. Therefore the flow is turbulent. Now the condition is what? The turbulent flow is there. Based on this Reynolds number, we have to choose the Nusselt equation. Nusselt equation. Okay, here in the Lamier condition, two condition I solved. One is the constant wall temperature, constant heat flux is forward. Now the condition is what? Turbulent flow. Turbulent flow. The page number you note on it, and also you note on this equation. Here fully developed flow 2.3.1 Ditters-Boelter equation is the famous equation to solve the turbulent flow in a pipe. This is the equation. Nusselt number is equals to 0.023 Reynolds to the power of 0.8 PR to the power of n, where n is what? N is equals to 0.4 for heating of fluids, n is equals to 0.3 for cooling of fluids. In our case, in our problem, the fluid is entering at 50 degrees centigrade and leaving at 70 degrees centigrade. This is what the fluid is get heated. Therefore, the n value becomes the 0.4 for the PR to the power of n. The same thing I taken here. The equation 2.3.1, I taken the equation n is equals to 0.4 for heating. Substitute the values. Reynolds number, you know it. Then you find out the Nusselt. Once you know the Nusselt, H is equals to di by k. You find out what is the H value. Once you find out H, the next is what? You have to find out the rate of heat transfer. Q is equals to HAS TW wall minus TM. I will write one more time. Q is equals to H into surface area wall temperature, T wall temperature minus T mean temperature. T wall temperature is 100 degree. T mean is how much? 60 degree. 60 degree. Substitute the values here and you will obtain 48 kilowatt as the rate of heat transfer. But in some textbooks you will get Q is equals to HAS delta T Lm, logarithmic mean temperature difference you will obtain. That is what delta T Lm is equals to delta T1 minus delta T2 divided by ln of delta T1 by delta T2. Okay. By using this equation, also you'll get the answer almost near to this one, and also by using T wall minus T mean, from this equation also you'll getting the answer almost the same value. These things will be discussed in the heat exchangers. This equation will be discussed in heat exchanger. Now according to my suggestion is, you can go for both the equation. Both the type of equation is given in the different textbooks. Which one is easy, you go through that one. For deeper learning, deeper understanding this one, I will explain the heat exchanger. This is the end of the seventh problem. Here what we learn means, once the procedure will be the same thing: collecting the data, find out the mean temperature, collect the properties, later find out the Reynolds number. Based on the Reynolds number, choose the result equation, find out the H value, find out the unknown value, anything. In some problems the Q value they will give, you have to find out the length. But in some problem they will give the diameter and length, you have to find out the Q earlier. Here this one should be note on here, how to calculate the rate of heat transfer. T wall minus T mean, or delta T Lm, where delta T Lm means this equation. These things will be explained in the heat exchanger chapter. Now we go for the next problem. Now this is the last problem from the internal flow. This is what, here the different cross-sectional area. A rectangular tube 30 mm cross 50 mm carries a water. The fluid is what? Water at a rate of m dot is given. Here once again u is not given, but m dot is given. Don't confusion about the m dot or a u. So many times I explained in the last three problems. Determine the length of the tube required to heat transfer from 30 degrees centigrade to the 50 degrees centigrade if the wall temperature is maintained at 90 degrees. This is the T wall, this is the Ti, this is T naught. In this problem, the properties is given in the problem itself. There is no need to find out the T mean and collect the data from the data handbook. But in this problem, already the data is given in the problem itself. Use following properties of water at 40 degrees centigrade. These are the properties they given: rho, Q, Cp, mu is they given. But in this problem, in this data, the Prandtl number is not given. Prandtl number is not given. We should find out the Prandtl number when it is required. Just I write the sketch. This is the rectangular duct. In the rectangular duct, m dot is given 2 kg per second, and the Ti is given 30 degrees centigrade, that is entering here. This is the exit. T naught is 50 degrees centigrade, and this wall temperature of this duct is T wall is 90 degrees centigrade. We have to find out what will be the determine the length. What is the length? You have to find out what is the length. To find out length, we require the heat transfer. To find out L, we required Q. To find out Q, H, Nusselt. To find out H, we required Nusselt. To find out Nusselt, we required Reynolds number. To find out Reynolds number, we required data. The same procedure for all 8 problems. What the 8 problems is solved, the same way. I will just consolidate the final terms. See, I already mentioned properties is given. Just I collected the data. Next is what? This is not a circular duct. This is the non-circular duct. So in non-circular duct, you have to find out the hydraulic diameter. This is very important. I already mentioned in the introduction of this problems, introduction in the internal flow while solving the problems. Hydraulic diameter is equals to dh, 4 into cross sectional area by perimeter. What is the cross sectional area of this one? This width into height. This width into this height. Width is how much? 50 mm. Height is, or the thickness is 30 mm. Find out the cross sectional area. Next is the perimeter. Perimeter of this one. Okay, total, this is the perimeter. 2 times of 0.3 plus 2 times of the 50 mm. 2 times of 30 mm plus 2 times of the 50 mm. So we have obtained as the perimeter as this one. Now you substitute the AS and perimeter to the DH here, means hydraulic diameter. You obtain this hydraulic diameter 0.0375 is the hydraulic diameter. Once you know this hydraulic diameter, now you use the Reynolds number to find out the Reynolds number, that is rho UMDH by mu. Once again I am repeating that for a non-circular ducts, don't use this equation. Don't use this equation. Here of course m dot is given, but you cannot use this equation. I will write here, don't use this equation. For m dot or m pi d mu, don't use. M dot is given, you have to find out the m dot is given, find out the um, then you find out the Reynolds number. Always keep it in your mind. Don't use this equation for the where non-circular ducts. For non-circular duct, this equation is only for the circular duct. Reynolds number is equals to rho into um dh by mu, but we don't know the um, so you find out the velocity by the mass flow rate. M dot is equals to rho into cross sectional area into um. Cross sectional area, we know that one, length into width into thickness. Find out the um. Substitute the values to the Reynolds number. Now you know all the values. Rho is given, mu is given, so Reynolds number you obtained as the 76,557. This is greater than 2,300. Therefore, flow is turbulent. And the next, once you know the Reynolds number, next step is what? To calculate the Nusselt number. But we don't know the Prudhomme number because Prudhomme number is not given, is the problem. But Prudhomme number is equals to mu into Cp divided by K. Just you substitute the values, you obtain the Prudhomme number. Prudhomme number is 4.3. And P to the power of n, the n is equals to 0.4 for heating and n is equals to 0.3 for cooling. I just explained in the previous problem. The same way here is the 0.4 because here entering is 30 degree and exit is 50 degrees centigrade. So it is the heating process. N is equals to 0.4 and I obtained the Nusselt number as 332.9. And the next is the H. Find the same thing. Here this is the hydraulic diameter, dh, hydraulic diameter. Dh is what? 0.0375. Find out the Q value. After finding out the Q value, once again Q is equals to HAS T wall minus T mean. T mean is what? Ti plus T naught divided by 2. That is how much? 30 plus 50 divided by 2 is 40 degrees centigrade. Once again substitute here, you will obtain the L value. In the previous problem, the L is given, you have to find out the Q. In the previous problem, L is given, you have to find out the Q, but in this problem, Q is given, you have to find out the L. The Q can be found out by this one because m dot is no, we know it, and the T naught and Ti you know it, and Cp is it is given here, mu Cp into T naught minus Ti. This is the end of the all 4 problems in the internal flow. See, for all the 8 problems, what is the procedure we found out? We did that one. What is the procedure we carried out? First, collect the properties, means collect the data. Based on the data, find out the mean temperature or the film temperature. Based on the film temperature, collect the properties of fluid. whether it may be water or a oil or a air. I solved all the three different materials. Next step is find out the Reynolds number using the properties. Based on the Reynolds number, choose the appropriate Nusselt equation. Find the Nusselt value. After finding the Nusselt value, this is the equation: h into length divided by k, or h into diameter by k, depend upon the whether it is the cylinder or a flat plate or a flow in a pipe. Okay, those things I explained in the last previous class, means previous problems. Find out what is the h. Once you know the h, the next step is what? Find out the q. Find out the q. This is the common procedure I used for all the 8 problems. Same procedure for the remaining problem also. You should solve the some different problems, but you should follow the same equation what I told, but don't get confused in the different textbooks. In the different textbooks they use the different data handbook equation, so you may get somewhat confusion, but always you use the what the textbook what the data handbook I referred, the Kodandaraman CP Kodandaraman data handbook should be referred. And also you take the equation from this textbook only, and you should follow what is the procedure I mentioned in the last 8 problems for the different problems. So you can solve n number of problems based on the this previous knowledge about the 8 problems. Thank you for watching the video.